Okay, well, why don't we start the, maybe I shouldn't say this, but the second half I'm sure you'll be much more boring than the first. What I want to do is talk about identification of social interactions. It's going to be based on this long, shall we say, handbook chapter that I wrote with Larry Bloom, Buzz Brock, and Yanis Ioannidis. And what I want to do is sort of give you some overview of where the identification literature is. It is a massive literature, and there are fundamental differences between nonlinear models, linear models, and the like. And so even though I grumbled that linear models are not the most exciting theoretical structures for social interactions, they are nevertheless the basis of most empirical work. And that's why I'm going to really talk in excruciating detail about the identification properties of these models. The other reason that I want to is that this is going to sound a bit strange, but from the perspective of parametric identification, which is a fancy way of saying where you have functional form assumptions, the linear models are actually the case where identification is most problematic. In other words, there are many contexts in which nonlinear models are identified, but the linear analogs are not. The intuition you should have for a result like that is that identification breaks down when you get, perfect correlation of certain endogenous variables which simultaneously appear as regressors. Well, one of the good things about a nonlinear system is it kind of gets rid of this these linear dependence possibilities, and so that's the metaphor, at least in a very loose sense, the reason why treating this as the baseline is useful, because if we understand identification here, we have the advantages both that it really is understandable because it can be reduced down to standard simultaneous equations arguments, and second, we have good a priori reasons to think that that other cases will be less difficult. All right, so oddly enough, even though I said this is going to be about econometrics, I do want to start with theory. Okay, now there's a reason for that, and it's the following, and that is, as I said, most empirical literature is based on the so-called linear and means model, and it's a particular representation of how outcomes depend on individual and social factors. And as I indicated in the last lecture, it is a model that sort of, when you start off, makes an extraordinarily strong a priori assumption, which is that you know a bunch about the nature of social interactions. But it's actually going to turn out to be a little bit more than that. And that is, if I started off as a reverse engineering exercise and said, I want to use a linear and means model, tell me what the microeconomic environment is that generates the linear and means model as an equilibrium, it turns out you don't get the model that's estimated in the empirical literature. You get a slightly different model. Okay. Now you might say slightly different, but why does that matter? It's because slightly different has to do with features of the mathematical structure where if you take a large sample approximation, you converge to something. Interestingly enough, identification is not a property that gets preserved when you take large sample approximation. So what it's going to turn out is if you do the micro-founded model, in other words, you don't do large sample approximations, identification holds even though the canonical model that's been studied in the literature, identification fails. So this is one of the cases where you have to really be careful about the details because you can get very different results. All right, so what do I mean when I say I want to start off by doing reverse engineering? What I mean is the following, is I want to get a linear regression and then talk about whether it's identified. So the whole thought experiment is going to say, yes, I believe in groups. In other words, I want to think about a case where the group structure was appropriate as prior information. Okay, so individuals are organized in groups. Each group has a population size, ng, so g is the group and n's the number of people in it. And so at the end of the day, I'm interested in individual behavior. Those are the omega IGs. And the reason that I use that notation is just so we can remember, because you always want to think of each person as a member of a group. I want to sort of ask, how do I get a linear representation of that behavior? So the answer is, the reverse engineering is a triviality, algebraically. And what I mean by that is that the thought experiment's the following, and that is you say, well, I'm going to think about an environment in which individuals have information sets. They are not going to have perfect information. You don't know, you can't look into somebody else's mind and know what their epsilon is or anything like that. And so by dotting the I's and crossing the T's on the information, I'm going to derive a Bayes-Nash equilibrium. I'm going to deliberately choose functional forms because I want a linear model. All right, so when I tell you that, in some sense, you could know what I'm going to do. Okay? In other words, what I'm going to do is say, people have some sort of quadratic objective. And the nice thing about quadratic functions is when you differentiate them, they are linear. Okay, and again, this is obviously with immense loss of generality, but the whole point is to get the regression at the end of the day. All right, and so what one works with are utility functions that look like this. So there's a bunch of notation, and what it says is the following. And that is the behavioral primitive, in other words, the payoff function depends on two terms. The first term is omega ig, or excuse me, theta ig, multiplied by omega ig. When I differentiate that, what do I get? Theta ig. So that's going to be the equivalent of the deterministic private utility and the random utility that I had talked about together. Okay, and I'm going to assume that they're additive. And I'm going to assume the deterministic part is a linear combination of observables. The second term, the minus omega ig squared divided by 2, is just there for convenience, because what that will do is make sure that I actually have a solution. Okay, so that's of no interest to us. And then the third term is the conformity effect that we've already seen in various contexts. All right, I have to, and I've used the world's worst notation because in the decision problem, the variable in front of the conformity effect, that's actually a script pi. It's not an omega bar. So it was a stupid choice. All right, so the whole idea then is to do the following, and that is to do a series of calculations that say each individual makes an optimal decision, in other words, chooses omega, taking as information his heterogeneity that I can also observe as the econometrician, or taking as given information he has, and that's where the I's are dotted and T's are crossed, which I don't have, but he has. But then being very careful to say there's something called epsilon ig, and that's information that's individual specific. In other words, you know that piece of your payoffs, but nobody else does. Okay, people form beliefs about that, but they don't know them. So the upshot is that when you do this exercise, you can go through and solve for individual decision problems that are linear in all the stuff that we want. You do what's called the method of undetermined coefficients. That's a fancy, you all know that from introductory rational expectations. What it says is you conjecture a linear solution, and then you ask, how does the theory constrain the values of those coefficients in such a way that the expectations agents are forming are ex post rational. Okay, that's an important point. These models take as the baseline a particular notion of rationality, which says that beliefs are consistent with the structure of the model. Now you could say, well, some of you would say they don't think that sounds like a good assumption. I don't think it's a good assumption, but the point is, again, it's a baseline, and then one can ask questions about how to relax it. All right, the only thing I want you to observe is this, and that is that one of the coefficients in this procedure actually depends on the group size. And you have a faculty member who's discovered something similar. Okay, but this actually shows up as well in the linear and means model. Now, I make a big deal about that because if we go through a bunch of substitutions, which would bore you stiff, would bore me to calculate, this is what we end up with. Okay. We end up with a description of individual behavior that says that my behavior depends on a constant term. We don't care about it. It depends on whatever contextual effects I'm using as in the model. It depends on my own characteristics. It also depends on the average characteristics of the individuals in the population, and then some sort of shock. All right, why did this other variable show up? Because the original thought experiment was, I want to conform to my beliefs about what others are going to do. Well, and then the only thing I need to know about what others do, by assumption, was what they're going to do on average. Well, I therefore need to know the average of the individual heterogeneity. All right, so lo and behold, we have a way of describing the linear and means model simply as the Bayes-Nash equilibrium for a quadratic loss function. Now, there's a minor technical point, which is under the assumptions that are delineated ad nauseum, which I skipped over. You can also prove that the equilibrium is unique. Now, that's trivial given the fact that it's a linear model, because at the end of the day, all you're doing is inverting some matrices. It also, just to be honest, it depended on the assumption that the unobserved heterogeneity, that the probability densities don't depend on the observable characteristics. Otherwise, I would have the problem of multiple equilibria because of weird self-consistent expectational paths. So it's slightly less obvious than it seems, but for our purposes, we don't have to worry about it. So there's not going to be a multiple equilibrium problem here. Okay, so there's a theorem that just says in the well-posed linear and means model, you can get an equilibrium description. And I'm sorry, with these quadratic loss functions, the equilibrium is a linear and means model. Okay, that's all that matters, and it's unique. Yes?
Can you go back to the specification of the equation? Okay, yeah. What was the last one? All right, okay, let's say that's it. That one.
Yeah.
Okay. So this is the end of the story, right? In terms of solving the model. This is what, now I'm the econometrician, and I'm looking, I have this model in mind that I was going to take on.
Well, no, well, I'm going to be very, let me go a few slides, then if I haven't answered your question,
okay. All right.
then throw your pencil at me, and I'll sue you for millions. Okay. So all I wanted to do was, and I know I do it very fast, was say there is a very rigorous way to end up with something called a linear and means model. The one observation I do want to make is that when you write down the Bayes-Nash problem, the way you think about a conformity effect is to ask the question, how do I deviate from the average behavior of others? I don't include myself when I ask what the average behavior is. Now you might say that sounds like a complete triviality. It actually is a non-triviality, and the reason for that is if I included myself in the average, then everybody would compute the same average that they compare themselves to. But by excluding myself, that means each person has a different reference set, and there's actually going to be variation in one of the variables in the system. That actually produces identification, strangely enough. Good. So this is the model that that is estimated in the empirical. Well, this is the model that's been conventionally studied in the econometrics literature and has received undue application in the sense that people ignore the endogenous effect. And so what the model says is that I've got some outcome, and I'm just say it depends on xi's, individual level variables, yg's, whatever these predefined groups are, and my belief about the expected average behavior in the group. Please.
So it's not always the average that is a relevant one, right?
That's an important, yes. And so the linear and means model is actually already, that was what I meant. It's with immense loss of generality that when people just stick in averages, they have taken a stance on the social structure that may or may not be a compelling one. Okay? So what
so for instance, you don't have cool kids and stuff. I mean, the cool kid idea cannot be captured here.
That's right. So this, yes, and so, and in the chapter, I hope we were obnoxious enough to keep emphasizing how strong the substantive assumptions are. It sounds easy to just stick averages in, but it really means something. But the other point I wanted to make is the way that identification has been studied in the literature is that it has ignored this distinction between my wanting to conform to others. What it says instead is I just care about what the average is in the population, and it includes myself. Okay, everybody with me? So that's the little difference between what the rigorous Bayes-Nash analysis would give you and the object that's being given here. Now, if the population size went to infinity, then it wouldn't matter, would it? Well, one of the messages is if you do that, that model has different identification properties than a model with a finite number of agents. So this is an example where what sounds like a trivial detail actually matters.
Is the problem if you just take a naive average then, in a sense, you'll be best responding to yourself?
Well, that's why it doesn't make any sense to put it into the Bayes-Nash problem. So writing down a coherent view of what it means to conform, since by definition you don't conform to yourself, you have to conform to yourself. Its inclusion here is theoretically weird. Okay, but this isn't a surprise because, again, the way the literature evolved was it didn't say here's a opposed microenvironment, what's the equilibrium? It said here's an equation, let's analyze it. All right, and so the idea is that people are reacting to their beliefs about the average behavior in the population. Now you might say, well, what if they actually observed everyone? The answer is, in this case, doesn't matter because then there would be correlation with the right-hand side variable. You'd have to use instrumental variables. They're already defined by the system, and what would you then reconstruct? The expected value of the variable given the x's. So in this case, from the econometric perspective, the distinction between saying the behaviors depend on expectations versus realizations counts for nothing. In nonlinear systems, the distinction would matter. All right, so let's solve for this okay, so there's assumptions on the errors. I want to start with the baseline case, which makes life easy, and that is that the errors are IID. So there's a messy way of saying that. That's how you say it. We want to relax that later on, but again, I want to take the model kind of under the best case scenario and understand identification. Then one sequentially relaxes assumptions, and then we see what you can still say. All right. As I mentioned, once you introduce these endogenous effects, or I haven't mentioned, this gives us two things we can call a social interaction. One is the presence of a non-zero D. That would mean there are contextual effects, and we would like to distinguish that from saying that there is a endogenous effect, because after all, we would have different substantive theories or interpretations to a social interaction that's driven by role models versus a peer group effect or information effect, so on and so forth. Yes.
So like when we got that consistency or the topic of the average equaling like the hyperbolic tangent.
Yeah.
So those terms we should think about as like the average, not including myself. And everybody agrees on that the average is not including themselves.
If you actually go through the details of the paper with Brock, because the way to think about it is H was taken to be constant across everybody, and epsilon was taken as constant across everybody, I killed off all the heterogeneity that could exist in expectations. So even though we derived the Bayes-Nash, the average of everybody except me had to equal the average, including me. Okay.
Oh, I see. So kind of. Okay. So you have insurance.
Pardon me?
You have insurance.
No, we did it on purpose because we wanted to talk about that equation. If we did it the other way, all we would do is integrate over the h's, and we'd have a series of equations. So there was nothing in the logic of the exercise that would require that h be the same across everybody. It's just it bought us a huge advantage, which everything melted down to a single equation, and we could draw pictures of hyperbolic tangents and talk about them. Yeah, but there's no issue with with having heterogeneity in the h's relative to our model. Okay, so the key idea is the following, and that is when I write down a model, what I'm saying is the behavior depends on various things, but one of the variables is endogenous. It's the beliefs that people have. It's endogenous in the sense that expectations have to be consistent with the model. Well, this is something economists do all the time. We calculate those things. So all you do is run an expectations operator through the system, and what you can show is what is the expected value of the average choice in the group? Well, it's just this equation here, k plus c, the average of the x's in the population. Notice I'm assuming people know the x's, plus dyg divided by 1 minus j. All right. So what that lets me do then is talk about the reduced form for the system. So remember the thought experiment, as I said, this is the assumed model I want to estimate. One of the variables is endogenous. I substitute it out, rearrange terms, and the regression model. So this was your, by the way, do you go by Joe or Joseph? I'm sorry.
Either. Joe.
Well, what do you prefer?
Joe, I guess. Joe is good. If you want to conform.
Oh, I have no desire to conform, but I want to know what your preferences are.
Okay, sure.
I'd say the minimum thing I think people are entitled to in life is to be called what they want. Okay. All right. So, anyways, this is the thing you actually estimate when you do empirical work, because it's now saying here's one observable, which is the outcome, and it depends on other observables. Now, the thought experiment, of course, then asks, can I recover the parameters from the initial model from the reduced form? This is, introductory econometrics. Well, let's think about it. Let's suppose that there were Rx's and Sy's. Actually, things look pretty good for identification because I have, I've got R plus S plus 2 parameters. But I've got 2R plus 1 plus S coefficients. And so even if there was only one of the R's, I would have as many coefficients as parameters. So that sounds like things are identified. M. Remember, that was the endogenous thing I needed to substitute out, so I have a reduced form, because the only thing the data can speak to, that's the only thing the data reveal. So the question is, given that I can estimate k divided by 1 minus j, c, j divided 1 minus j, and then d divided by 1 minus j, can I from them recover k, c, d, and j? Okay, so as I said, this is a very old-fashioned problem.
Now, all of these is being assumed the group.
Yes. So I'm doing the best case, which is the groups, there's random assignment across the group, so I don't have to worry about the errors not being IID or being correlated with the errors. Okay. So, as I said, most of the empirical work, unfortunately, does this. So let's see what the problem is. If you read the Mansky paper, which introduced the reflection problem, he made an assumption on the relationship between x bar and y. Remember, the general form was omega depends on x bar g and y. And so that's why in the reduced form, you had one set of regressors called y and another set called x bar g. So in Mansky's paper, he has actually made an assumption, an additional assumption. He assumed they're the same thing. In other words, the way he constructed his contextual effects was to say that every contextual effect is the average of an individual level variable. So that creates so in other words, there's a one-to-one mapping between them. For that special case, it must be that mg, the expected average, is some linear combination of the y's. And so by inspection, identification has to fail. Why? Because m and g, m is linearly dependent on the y's, and therefore there's no way to disentangle whether your behavior is determined by M or it's determined by Y because they move in lockstep. Okay, and that's what he meant by the reflection problem. You can't tell if it's the face or the face in the mirror. They're the same thing. Okay, so that is the entire basis of the reflection problem. And so one can give a theorem. And when does identification hold? Notice there's no reason a priori that Y has to equal X bar. In other words, that's a substantive assumption. It says the only sense in which there are contextual or group level effects is that this particular phenomenon happens. All right, so the theorem on identification in the linear and means model, and this is due to Brock and myself, which is actually very simple to state, and that is if you want identification, you need this to be true. All it is saying is that if I project the behavior on the Y's, I get a different answer than if I project it on the Y's and the X bars. Because once there's a difference between those two, I have a way of discriminating between movements in M and movements in Y. Okay, so it's a one-line proof. And anyways, this tells you a sufficient condition. It's not necessary. It's a necessary condition. It's not sufficient. It's the distinction between rank and order conditions and simultaneous equations. The second part's not interesting. Go ahead.
So if you had a specification that the individual level effect entered in non-linear, but then the contextual effect entered in just as linear, then just that functional form assumption would be the identification.
Yes, that would do it for you. So this actually has now there's a way you can say what's needed for identification. I need at least one individual level variable whose group level analog is not appearing in the Y's. And you just gave that because you took a nonlinear transformation of an xi and said it's averaging in the system. Okay. So now we can now you can understand what drives the reflection problem. It's this assumption that, well, first of all, it only applies in linear systems. That should be, we'll see in a second why that's obvious. But the whole point is that it was based on this assumption that there was a one-to-one mapping between the individual effects and all the notion of social influences. Yes.
More of a comment. Like, why do people push back more on this? Because like whenever I talk about social interaction, people are like, oh, you got to think about an NCA reflection problem, and they make it seem like a really deep thing. But like what you're saying here, he made this pretty.
So now you're going to make me sad since we proved this 11 years ago.
No, I think the reason why is like people focus a lot on the tractability of the model that you showed and wow, this is really cool. But then in a sense like they don't read the second half of the paper which focuses on identification. And so like they look at and in a sense I'm saying like why don't people push back more on this reflection critique? I don't remember if you do that in a very like directed way.
Well, as the result's been around for 11 years. I pushed as hard as I felt comfortable. It's not my style. All right. Okay, but all I want you to know is there's actually a way of thinking now about when the reflection problem holds and when it doesn't hold, and it's something you can compute using aggregate data, and it's completely intuitive. All right.
Yeah. So this, when I think about the linearity, right?
Mm-hmm.
I mean that's the way I saw that problem. That's the rank condition, right?
Mm-hmm.
Essentially, this is the order condition.
No, this is the rank condition.
Okay.
That's what it says requires.
Right. So it's essentially the same concept. I mean.
No, the order condition is just. I'm not sure I want this.
No, sorry, between the rank and order, but I would say what you need is for the no linearity between the variable that is your contextual effect between y and x bar.
Yes, but the sense in which but what you need it so you need this to be non-zero. If certain coefficients in the system were 0, this could still be 0 even if they didn't obey that. That's why it has to be written this way. I need the leverage to distinguish the m from the y's.
Okay.
So that's the why I'm gonna push my formulation, particularly since Peter says I'm not aggressive enough. Okay.
I'm not saying that it's just I'm not saying that it's just your responsibility. Maybe it's a shared responsibility of this community. But I mean, it's just kind of I guess I was just a little bit like when you showed me this, I was a little bit irritated that people kind of like make it seem like the reflection fatigue is this really big, impressive idea when it's. Sorry.
So you found out the hidden agenda. We organized a summer school so I could get 30 people to walk around saying, oh, you should read that other paper. Okay, let me press on. I want to distinguish now. I just want you to keep this model in the back of your minds. And that is what I'm calling the general model. In other words, if I wanted to work in linear systems, and I didn't want to take the very strong stance of the linear and means model, a way that I would think about it is to say that my behavior depends on some linear combination, things about me, things about other people, and behaviors of other people. Now, in a subsequent paper, we relax the assumption those two are the same. I could allow for distinct coefficients in how I weight your characteristics versus your behaviors, and so that and there are analogous theorems. Everything I say, I kept this just to keep life simpler. But this, in some sense, is the social networks model. And again, I wanted to emphasize the linear and means model as estimated as a special case of this, where you have this block diagonality, and you have ones on the diagonal of the matrix for all the weights across individuals. Okay. So at the end of the day, we're going to be interested in knowing, can you estimate this creature? Because this is the very general one. And the answer you already know is not without some prior knowledge of what the social network is like. Now, to distinguish between the micro-founded model of linear means and the one that's typically studied, you can think about two types of averaging, and this jargon is due to Moffat. You can think of exclusive averaging, where I exclude myself and I average over others. And that would restrict the coefficients in this way. And what Mansky's paper did was inclusive averaging, which restricts them this way. All right, so here's a theorem. And this is a case where the theorem, 98% of the credit should go to Lee, Bramoulet, Jabari, and Fortin, co-authors of mine and my. We will take 2%, only because we have a slightly different version, which I think is cleaner. But the point is that they basically figured it out. All right. And so here's the point. It turns out that in the linear and means model, with exclusive averaging, in other words, the correct model from the micro perspective, as long as there are at least two groups of different sizes, the model is identified. Identification fails under inclusive averaging. Now, Hedwig has probably seen something like that before. Brian Graham has an analogous result for a model where there are no contextual effects and and it's based on simply the covariance matrix of the y's. It turns out the idea of the group size being useful for identification is ubiquitous. Okay, so and so, what Graham did was he asked the question, suppose that I, by assumption, say there are no contextual effects, and by assumption there are no individual effects. So the only thing I can do is say omega depends on j minus omega plus epsilon. What he showed is that if you could look at what he called variance contrasts, that if you have multiple group sizes, you could recover j. What we're showing is multiple group sizes for the general linear and means model, not just the one where I set some parameters equal to 0. That's sufficient to achieve identification. But everything depended on excluding the individual from the averaging.
Is the idea that the difference in group size is going to kind of denote the variance?
No, well, that's what happens in his paper. What happens here is when you write down the coefficients in the linear and means model, because you're taking averages, those are just the sizes of the groups, right? You're adding stuff up and you're dividing by the ng. Well, you transmit that over to the coefficients. When I regress your behavior and the behavior of everybody else, the coefficient now depended on ng minus 1.
More in regression with smaller densities in the sense of smaller groups?
No, you don't want to say it that way. What you want to say is you get more precise estimates. Now, Art brought up a great question. So this says you get identification as long as you have multiple group sizes and you're being careful not to take the large sample approximation. See, Mansky's is the large sample approximation when n goes to infinity, because all infinities in this case are equal. In other words, they eliminate the notion of heterogeneity across group sizes. Aric's question has to do with, and this is an incredibly important point, and that is identification, remember, is a binary property. Either the system is identified or it's not. But as empiricists, that isn't enough. The question is, what can the data tell us? If I said to you, my God, the system's identified because I have one group with 1 million people and one group with 1,000,001 people, that may not help. Okay, and so one thing to keep in mind, and I'm serious about this, is that the identification literature tends to think in this binary fashion and doesn't pay adequate attention to issues of accuracy or precision of estimates. So the correct statement on the identification problem, on the reflection problem, is not that it should be thought about as an issue about identification. It should be thought about in the context of implications for the precision of estimates. All right, everybody with me on that? Pardon me? What was wrong?
No, nothing was wrong. I just didn't understand that last time. Why is it like this?
Because getting actual, because when you sort of write down the microfounded model, you don't get collinearity of M minus IG with the rest of the variables in the system, but you can get near collinearity. That should be the way to understand what is getting preserved after you do things quote unquote correctly.
So it's the idea that since you're identifying off of just taking one person from the group, like
Yeah, but yes, there may be. Right, and so remember what I said before, that one of the differences between inclusive and exclusive averaging is I have a variable that varies across individuals. Well, if there's a lot of people, it won't vary very much. Yeah.
So if we have groups of different size, that implies that you have, in a context of peers, like peers that are excluded from the groups of one others. Right?
Well,
so is the identification coming from those excluded peers?
Well, remember we initially started with a group model. It said that things are block diagonal. In other words, this classroom has within classroom interactions nothing across. This classroom interactions nothing across. The linear and means model is a group-based model. And so what I wanted you to see was that the Graham intuition, which you initially established for the special case where there was nothing except endogenous effects, actually applies to the entire linear literature. As long as you have multiple group sizes, you get identification. Yeah.
So it seems like the sort of argument you're making there was the question of weak identification. I mean, what I'm not worried about the range of my DNS, right?
That's fine. If you want,
right?
yeah.
But I mean, in some sense, our asymptotic theory is built in the notion of what that will give me. If that's true, then I'm also going to get a very large variance in my estimate.
Well,
so if I have bad data, if I have uninformed data, that will come out of the system.
Well, I would like you to be a little careful only because the point of the weak identification literature is that in finite samples, there could be problems.
Okay,
yeah, I'm sorry. That was the only modification I make to your observation.
Right. I just, something like Brian Crane's technique, you would see that, I've got a sample of people with variation which should be able to derive like this.
Well, I think you could, given a data set, you would know when you should be worried about it. But the point I want it to emphasize, despite Peter's unkind remarks, is the reflection problem should be recognized as a very serious issue in estimating these models. It's just the perspective I want you to take is not an identification perspective, it's a precision of estimates perspective. All right. So this is just going through the argument, and the upshot is that the message here is one has to be careful about taking large sample approximations. Okay, so even though if you sort of said predict the behavior of the system, the large sample approximation does perfectly well, it actually altered the identification properties. Identification is not something that follows the limiting, the large sample approximation. And so that's the main point that would have been missed in the literature. Okay, so that was the first message. The second message is the following, and that is there is something special about the linear and means model with respect to linearity. So consider a partial linear and means model. And you know, it's not an uncommon thing in econometrics for people to estimate partial linear models. You may not think it's the mean, it's some transformation of the mean. It may really matter whether the mean's below a threshold or above a threshold, et cetera. So a way that you can analyze those systems is to basically say, well, suppose that there's some function mu, and so that we induce a nonlinearity. If you know mu, you can prove that identification occurs, quote unquote, generically. Okay, the reason for that is nonlinear and means models, just simply, even in the large sample approximation, it can't arise that you have this linear dependence. That's what the nonlinearity buys you. Now, when I use the term non-generic, what I mean by that is the following. You think of a space of candidate objects, all the possible mu's, you know, and these are going to be twice differentiable functions. All right? There's going to be a subset of such functions such that a Bayes-Nash equilibrium can exist. So think of that as my initial set of candidate mu's. I then ask the question, for which mu's does identification hold, and for which mu's does identification fail? If I can show, and that's what the proof does, that the set of mu's where identification fails is of strictly lower dimension than the initial set, then I call that non-generic. So metaphorically, if you draw a box and I put a line through it and said those are the points where identification fails, that's I would say it's a non-generic property. Okay, now there's a very specific way that one would mathematize this notion of genericity, but the intuition I want you to have is that is this notion that relative to the initial set of candidate objects we might study, the set where identification fails is lower dimensional, and hence probably not worth considering, unless you have a very strong prior that one of those models is true. All right. Okay, so given time, so comment number one is, once you introduce nonlinearities in the systems, no reflection problem, even if you don't properly specify the underlying decision problem. Comment number two, once you introduce dynamics, no reflection problem. Now, why would that be? Okay, so here's an example of a backwards-looking system where I say my beliefs at time t-1 have some consequence for what I do today. Well, what I would do is I would recursively substitute out that expected value. So my reduced form would do what? It would have the entire history of the x's and the y's as elements of the reduced form. But notice that the structure of the model, that doesn't change the number of parameters, it's just recursive substitution, so I'm getting like beta, beta squared times stuff, et cetera. And so once you have a backwards-looking dynamical system, it's obvious that identification is going to generically hold.
Can you say that more simply?
Oh, when you have a backwards-looking system that looks like this, what's going to happen, I could replace mg minus, I could take the expected value of this system, right? Well, then I could do it at t-1, and then I could substitute it in for that term. What's that going to depend on? Those variables all backdated one term. So now I have a bunch of other regressors, but no change in the number of coefficients. And so once expectations enter with a lag, it's obvious that identification holds simply because when I compute the reduced form, and the way you would do it mathematically is you would multiply m by a lag operator. So you would re-express that as L, lag operator, times mgt. I would take the expected value of both sides. I'd have mgt there, L, mgt there. I'd pull it over, I'd divide, and you're finished.
Can you say...
In fact, I did it right.
There's no reflection product, and there's no simultaneity.
Well, I could have simultaneity as well, but as long as as long as I have the lag, that's what's going to buy it for me.
If you have the lag and the...
Yes, then things will be fine. That was what I verbally described before. That's the thing I would substitute in. Notice that's an infinite sequence. Now, of course, since we're at Chicago, we have to also think about what if my behavior today depends on my beliefs about what the population is going to do tomorrow. Well, in linear systems, that's typically done by saying my behavior depends on beta times my expectation of what's going to go on tomorrow. That is the Hansen-Sargent model, and it's well known what the answer is to that. And once again, identification holds. So, what's the message from first two messages? Okay, so three messages. One, do the micro foundations for the model. The economically justified model is identified as long as there's group size variation. Idea number two, regardless of that, if there's nonlinearities in the system, identification will generically hold. Idea number three, you also have identification when expectations, either in terms of lags or leads, come into play. And the reason for that is it essentially generates many instruments, and this is not my snide comment, these are instruments that are implied by the model. And that's the beauty of rational expectations econometrics is that you write down a system, and what that system says is some linear combinations of objects must be a forecast error. It hence has to be orthogonal to stuff. Those all become instruments essentially that you can use in the estimation. So that's why you could say the defect of the model is it makes so many assumptions. Well, the beauty of the model is it makes so many assumptions. It tells you exactly how to estimate it, how it should be estimated. All right, since we had some sociologists here, I did want to tell them that, and actually more importantly, since we have economists here, you should be aware that the linear means model is not the preferred specification in sociology. The way that's, and you are entitled to object if I exaggerate. I may snap at you, but you're entitled to object. Information is good. Okay. All right, so the serious point's the following, and that is that in the sociology literature, a popular technique is what I'll call a hierarchical model. And so the idea there is not to say you've got these social factors and you add them into the initial regression. It's rather to say that each social context defines a distinct linear relationship. And so there's a hierarchy. In other words, first you specify how coefficients depend on social context, and then you substitute that back into the first equation. And so what that means is that, so my assertion is the following, and that is that this would be kind of a way that a hierarchical model would function. In other words, I would say that for a given group, there's an outcome, there's a group-specific constant term, and there's a group-specific set of coefficients that apply to the individual effects. Then you append to it equations that look like this, that basically say that those coefficients, in one case a constant, in the case a vector, depend on, for us now I'm going back to economies, contextual effects and endogenous effects. Now in the sociology literature, they also would introduce random effects there. I dropped them because they don't affect identification, they just would add algebra. And I think there's already enough. Okay. But you see how the logic of the thought experiment differs? So this is part of, a message. Economists and sociologists need to talk to each other more because we don't even talk about neighborhood effects the same way. So even if we take the desiccated view in the sense of what algebraic linear equations do we write down to describe neighborhood effects, they don't even have the same form. So a natural question is, which I'm sure you're dying to know, is, well, is this model identified given all the stuff I've had to say? Well, pardon me? Oh, yeah, these are the coefficients on the y's. So the idea is each neighborhood has its own set of YGs. And so I need to take some linear combination of those to get the vector of coefficients that apply when I map individual characteristics to individual outcomes within the group. So psi has to be a matrix.
That's really complicated. Can you put that in terms of the actual attributes, maybe the percentages?
Okay, so an example, I don't know if it's empirically of any importance, would be to say the relationship between parental education and offspring education, that coefficient depends on the average education in the neighborhood. Okay, that's different from saying I add average education to the neighborhood as an additional regressor.
But at the end of the day, if you substitute, it's going to be very similar.
Well, that's what I'm going to do. You're right. So that's why it's very easy to analyze. We already have the math for it.
So in a sense, kind of like, it's saying that the return to like some group-specific attribute.
The return to some individual specific attribute depends on the social context.
Okay.
All right?
So it changes the way that we should think of the coefficients. So in a sense, it embeds some notion of like complementarity into the coefficients themselves. I don't want to say complementarity because that's a statement about a value, whether something's positive or not. It involves an interaction. That's the key. So do the substitution as suggested, and lo and behold, the hierarchical model looks almost like the model that which we spent all our time worrying about. Now, here's the happy news. That's nonlinear. So we're done. In other words, you could formally prove that all of the hierarchical analogs to the linear and means models in economics are identified. It's because the logic of the model has a nonlinearity that is induced when you do the substitutions. So Leonardo's intuition was exactly right. Oh, absolutely, because if you took this model seriously, literally, that's the form that the interactions have to take. I mean, so there are restrictions there. Now, I don't know the hierarchical models literature well enough to know if there's nonlinear generalizations, but if we're in the domain of linear models, we have very tight restrictions. And I only brought that up so I don't want to make comments about identification for nonlinear hierarchical models because I don't know. All right. So, upshot of all of that argumentation was that if you take this alternative perspective on how to think about social influences, which is that they're mediators as opposed to additive objects, it actually, from the perspective of identification, it's very helpful because it induces a nonlinear system using the stuff that we work with, and you can show the generic identification holds. Would you have to, like, because in a sense that kind of like assumes like a mechanism, right? When you say these social influences are mediators, so like in addition to just showing identification, like in the empirical exercise, would you also need any robustness checks to kind of like validate that mechanism?
Well, that's too hard a question, to be honest. I don't mean that facetiously. What I mean is, you're asking when I specify the equation that describes how coefficients depend, is there additional information I can use to say that that's a sensible way of describing the dependence? And I would say the answer to that's the same answer is to why did I decide these y's ought to be in the system? In other words, that's where judgment, prior information comes into play. Remember, they say we have a priori decided these are the contextual effects, or the, if you believe it, endogenous effects that influence the coefficients, and then we move from there. But so I don't think there's anything that they have to do that we don't have to do also. Okay. Can you talk a little louder, please?
Is there empirical evidence that sustain the position of the hierarchical models in terms of like these?
Well, there's many papers that have estimated this structure and argued in favor of various group effects. Has somebody done a horse race to see whether one perspective versus the other is appropriate? I'm not aware of one. There's a certain sense in which I could, if I'm clever, or not clever, if I'm general enough, I can make the hierarchical model nest the economist model, and so it'd be very easy to do. It would just be a test as to whether certain terms appear or not. I'm not aware somebody's done that. And if I do it and I find that all the terms drop out, will you guys convert?
We'll leave it.
I said if we estimate the model and all the terms that that are required for the sociological perspective don't appear, we convert to the.
Steve makes me do the other kind. He likes the.
Oh. Well, his heart is in the right place. Okay, no. Okay, the serious point is there is no theoretical reason why you should think one way versus the other. And I want people here to be aware that, in fact, there's a disciplinary difference even in how you specify the regressions. And the thought experiment is, has a certain substantive difference to it. And that's a sort of example where economists and sociologists really do need to talk to each other more. All right. Everything I've had to say is was the pristine case, because I said I have IID errors and they're orthogonal to everything. As I mentioned before, we now want to ask the question, well, what do I do? I want to relax that assumption, obviously, but I want to relax it in two ways. The first way is to deal with self-selection. Okay, that's kind of the natural thing to be worried about in these environments, is you say to yourself, well, these groups, if they're endogenous, then the issue, it's fine to say that the errors got all realized independent of one another, but once people collect themselves into a group, that maybe people with high epsilons chose to be in the same group together, or people with low epsilons couldn't join their group because the house prices were too high, so on and so forth. And so self-selection is an obvious issue that arises whenever one estimates a social interactions model. Okay? So one approach, obviously, is to use instrumental variables. You say that, so what self-selection does is it says that the conditional expectation of the errors given the regressors after this endogenous group process is no longer 0. And so one strategy would be to find instrumental variables, objects that are independent or are uncorrelated with that expected value, but are correlated with the things you want to estimate. Okay. The difficulty, well, the advantage of that is that lets you be clever and think about quasi-experiments and the like. The disadvantage is that it's hard to think about a context where the instrument really would be orthogonal to that expected value of the error. Okay. Now, one answer to that is that it may be the timing can help you. In other words, there may be something that wasn't known at the time the groups are formed, but it occurred afterwards. And so from the perspective of the group formation, that couldn't have been part of the information set, hence cannot be part of the conditional expectation. So so all I want to do is just make two grumbles about the nature of instrumental variables, but that does not mean obviously it's an essential technique for empirical work. However, this time I want to be a real hardcore economist and say the following, and that is, from the perspective of economics, self-selection in some ways is the problem we should relish working on, and the reason for that is, what do economists like to model? Choices. And the whole point of self-selection is to say that people made certain choices that invalidated the statistical assumptions associated with a particular model. So the instrumental variables approach says, well, let's figure out a way to get around it. The alternative would say, let's embrace it. And that means, why don't we say, so when I say that we should embrace it, another interpretation of saying there's self-selection is to say that the model that I have specified is inadequate, and what I need to do is simultaneously model the process by which groups form and the process by which behaviors occur conditional on the groups. Okay, and so that's an alternative way of thinking about how one would address the issue of self-selection. That, by the way, is the Chicago approach, and more seriously, that's the Heckman approach. So the so-called control function approach to dealing with self-selection says the following. That is, you construct an auxiliary model of the process by which the self-selection occurred. That lets you construct a synthetic variable which captures that non-zero expected value piece. You stick that in the regression. That soaks up all of the problem that we had initially, and the remaining residual really is orthogonal to everything. Okay? Now, in some cases, this may not be feasible. In Leonardo's case, I can't conceive of a way to construct the control function for the sort of networks you were studying. But in other cases, I can conceive of it, such as neighborhood models. And why would I say that? Because after all, I could think about a model in which you had a multinomial logit for neighborhood choices and then linear models for the behaviors afterwards. So again, it depends on context, which is the appropriate methodology. So, yes?
And then, like, also, like, in some cases, like, there isn't self-selection, there's kind of like selection that's imposed on people. In case of segregation, you can only go here and you can move it.
Okay, so no, that's a fair comment. But remember, in econometrics, the phrase self-selection includes that. It doesn't, it's not a volitional statement.
How? But I mean, it's not, so, I see, so you'd say this is the person's choice given this constraint?
Yes, and the constraint doesn't let them do anything. But okay, no, I'm not. My only point is that that phrase you're giving it substantive meaning which isn't there. It's just a statement that after the groups form, the conditional expectations of the errors no longer obey the conditions because of the process of group formation. All right, and so the message I want to get across is that the alternative strategy is to simply say, estimate a richer model, account for both the process by which groups form and the associated behaviors in the groups. All right, now is one better than the other? As I said, that's not a meaningful question because it partially depends on whether you can do it, and it depends on what the data are, what data are available. Now, I'm not an instrumental variables advocate, so let me avoid that. What I do want to say is the following, and that is, it turns out, here's the interesting part. If you take the second route, in other words, you model both the process by which neighborhoods form, or groups form, and the behaviors in the group, that can help with the identification of social interactions. Now, the intuition is very simple, and that is one of the reasons people choose groups is because of the social interactions that are going to occur in them. And so the second behavior helps triangulate the presence of the social interactions. Okay, so there's an intuition. Can the algebra reveal exactly that same phenomenon? The answer is yes. I can't hear you, I'm sorry. Well, I'm about to. So I want you to start off with an intuition that if I know how groups form, if I have can sort of describe both how groups form and and describe behaviors in groups, that knowing both of those could help pin down the nature of the social interactions. And the reason for that intuitively is that this social interactions influence group formation. Okay, so all I wanted right now is an intuition. Now I want to give you literally just a piece of algebra. Okay, so a way to think about what I called the control function was to say the following, and that is I get some estimate of the conditional expected value of the error. Okay, and I can't actually estimate it, but I get up to some constant proportionality kappa. So I treat that thing that's proportional to the error as an additional regressor. That's the two-stage procedure. You just stick it in there. Once I've done that, the new error in the model, xi, obeys all the conditions we want. In other words, it is orthogonal to everything in the system, since by construction I yanked out all the violations. Okay, so that is, okay, so you can say that there. That's how you solve self-selection using a control function approach. But here's the cool part. And this is where you can see exactly how it helps with identification. Okay, what was the first observation I made about the linear and means model? Or not the first, but the observation that even if one doesn't distinguish between inclusive and exclusive averaging, what was a key condition for identification? The existence of an individual specific variable whose group level analog does not appear in the model. Well, lo and behold, when I do the selection correction, what did I just add? An individual level variable whose group level analog does not appear in the model. Okay? That presupposes that the way that the selection works depends on my characteristics. An alternative could be that the selection correction only depends on like the expected behavior in the neighborhood. Maybe that's the only thing that everybody cares about. Well, if that's the case, then the selection correction would do what? Actually, I don't like these slides. I'm just going to skip them and say what's in them. It would add a term that's a nonlinear function of the expected value. That was the second example where identification held. In other words, self-selection turns a linear means model into a nonlinear means model. So either by adding this additional individual specific regressor, which of course really the theory does say shouldn't appear, its average shouldn't appear there, or by inducing the nonlinearity, we can now go on these two routes towards identification. Okay, and so the reason I wanted to say it in a certain order is I wanted to see the intuition is additional behaviors help triangulate. How do they do it operationally? It was by putting us on one of those two paths where the reflection problem didn't apply. All right, and so I like that example because if there was random assignment across neighborhoods and YG equaled XG, identification would fail. But if there's selection on unobservables in the neighborhoods, even if YG equals XG, identification holds. So that's an example where randomization actually would adversely affect identification. Now, of course, it's a rigged example, and it's not rigged, but it's because the thing that randomization costs me is the observation of the additional behavior. So the big message is we are good at modeling choice. I mean, that's what that's our business. That's what we're. And so I think that there's been inadequate attention to using neighborhood choices as a mechanism by which one can uncover the presence of social interactions. All right, now there is an additional, okay, so that's kind of problem number one. The second problem is what to do about unobserved group effects. So if I rewrote these models and I put in a term called alpha G, well, that makes life very difficult because unlike the self-selection case, if I just say there's group level unobserved heterogeneity, I don't typically have a theory of the nature of this group level heterogeneity. So I can't use economic reasoning or maybe say more broadly social science reasoning to pin the thing down. And so I have to think about purely statistical fixes, as it were. So one strategy would be to actually use panel data and difference it out. And if you're working with binary choice data, you have Chamberlain's analogy to differencing in discrete choice contexts. So that's one answer. Of course, that presupposes that the unobserved group heterogeneity is time invariant. A second possibility would be to assume that the group level heterogeneity is a random effect as opposed to a fixed effect. And that's actually what Brian does in his paper. Because what that does is it says something about the relationship between the idiosyncratic error and the group level error. And you can exploit their orthogonal under the random effects assumption. And you can exploit that to achieve identification through covariance restrictions. Okay, but what I want to say is in linear models, it's very hard to deal with unobserved group effects. And that's I'll say one of the frontiers where more work needs to be done. Happily, in nonlinear environments like discrete choice environments, there's much more you can do. Okay, but the linear model in this case really is the worst case for unobserved group effects. And I don't have any much to say outside of the kind of the standard arguments, differencing instrumental variables, use a random effects assumption, and then augment the classical simultaneous equations analysis, which is based on exclusion restrictions with restrictions on the variance-covariance matrix of the reduced form errors, which is the Graham approach. Okay? I do want to make a couple of comments about a literature that has argued that you can use contrast between individual and aggregated data to uncover social interactions. And so this is the so-called social multiplier literature. Roughly speaking, the idea is the following, and that is you compare two regressions. At the individual level, I run a regression of outcomes against x's, and I get a coefficient b. I can do that within and across groups. Then what I do is I aggregate the groups, and I regress the aggregate in the group against the average of X. And the argument is that what they call the social multiplier is the ratio B hat to B. And so the claim is that when I've aggregated up, I see kind of what the overall effect is of changing the X for everybody, as opposed to the first one, which only tells me what happens when you change the X for one person and keep them constant, and that should reveal something about social interactions. Unfortunately, that's not a good way to go. The reason for that's the following. That is the reduced form for their model. So what they do in the first regression is they've omitted a term. If I said to you, what is the expected value, or what's the probability limit of this coefficient, I have no idea. It depends on the covariance of xi and x bar. So it would depend on what the sampling scheme was in choosing across neighborhoods. And so the handbook chapter goes through examples where you could get a social multiplier that's less than 1. It could do anything, in other words, but it's only an artifice of what the sampling scheme is. So, so now I will make a strong statement. I think this is not a good way to go. Okay. All right. So.
Is that connected to the fact that you're also dealing with a number of factors, trend effects?
No, this was all cross-sectional, so there's no notion of a trend.
No, I mean, I shouldn't say trend, but I mean like slope effects.
No, it's really just the fact the first regression is misspecified. It's an incorrect model. And so I can give you whatever, depending on what the covariance structure is of the omitted variables with the included variables, I can get anything you want. All right. What I want to do in the remaining 15 minutes is talk about general social networks models. One of the things I've tried to emphasize over and over again is that the linear means model and even the hierarchical model are taking very strong assumptions, making very strong assumptions about social structure. And so, in some sense, I could have said, I'm going to skip all of this, and I could say that this is really the model that I want to think about. Okay, and this, I showed you this before, and I am going to make very strong assumptions in terms of, I'm not going to worry about the endogeneity of the network. I just want to say there is a social network. Now, this is a rich social network because it isn't an adjacency matrix saying who's connected to who. It's also saying what the intensity of the connections is. Okay, so this says it's meaningful to say somebody's your best friend versus your fifth best friend. And so obviously through previous arguments, both the inclusive and exclusive averaging were special cases where you assume you know the values of the A's. Okay? So a way to understand the linear means model is that it assumed a gigantic amount of information. In other words, it told me what that matrix A is, ex ante, and it just gave me these intensity parameters as the residual objects to study. So that leads to the following question. What if I knew, okay, so first of all, it's going to sound a little goofy because because data sets don't really come in this form. Let's suppose that I was willing to take an a priori stance, or the data somehow told me what A is, but it wasn't the linear means model. So now we have a question. For the class of candidate social networks, of which the linear means models of both forms are elements, does identification hold or not? Well, it's going to depend on A. We already know there's a case. We already know there's one case where it does and one case where it doesn't. So there's a nice theorem in the literature which is due to Bramoulet, Jabari, and Fortin, in which they give a condition on that socio matrix A. That's what for identification. Now, one thing is you need I minus JA to be invertible. The reason for that is otherwise there wouldn't be an equilibrium. So that's a trivial restriction. So what they're able to show is as long as basically A to the 0, the identity matrix A and A squared are linearly, they aren't dependent, that identification holds. So that's an easy thing to check. So this is the key thing. So what do we know? We know that one case of the linear means model identification holds. We know one case of the linear means model where it fails. We have a condition now that tells me for an arbitrary social network whether identification holds or not. Okay. So now I want to know, well, is it common or uncommon? So the way to think about that's the following. And that is, okay, without loss of generality, because obviously I can always renormalize, I'm going to assume J is in the half open interval 0, 1. And I'm going to define by S the set of all matrices A such that I minus J is invertible. Okay, everybody with me? The population size is NV. That's an important difference between thinking about groups and thinking about a social network, is that you think about the entire population and groups are just a special case where you put zeros in a lot of places. All right, and so happily, what do we know about any matrix? I can always just stack the rows or stack the columns. Either way, I can always think of each of these matrices as a vector in R NV squared. If NV is bad, then NV squared sounds terrible. Okay, so here's a serious point. Okay, I can think of the set of all matrices A such that an equilibrium exists. I can then ask, within this set, characterize the set of all matrices such that an equilibrium exists and identification fails. Theorem. Identification is generic. What that means is that when you define these subspaces of R using either polynomial inequalities or sequences of polynomial inequalities, they're called semi-algebraic sets. So they're very easy to analyze. They have nice smoothness properties. So figuring out the dimension and all that is not a problem. What you can prove is that the subset of non-identified social networks is of strictly lower dimension than the set of the matrices such that equilibria exist. So that's the sense in which identification is in fact ubiquitous. And so strangely enough, the linear social interactions literature focused on a non-generic case. All right. Now, why do I make a big deal about this? Well, it's simply because we don't have enough knowledge to say, have detailed information to say something like this is the right sociomatrix versus another. And so we care a lot about the fact that, that the non-identification results are going to require that you really believe that you know the sociomatrix. And so this is kind of the big result that Bloom, Brock, Ioannidis, and myself came up with. The result also holds if there are separate sociomatrices for endogenous and contextual effects, so that it can be quite easily generalized. Please.
So this is, in some sense, a generalization of the second result it shows, which is before the groups are different cycles and all the identifiers that the groups is just being block diagonal.
Right, and this doesn't require any block diagonals, anything like that. It says that all the possible candidates, including all the non-block diagonal ones, yeah. That's the set of candidate social, subject to existence, that defines the set of candidate sociomatrices.
Right, yeah. Sorry, I
okay, and so I want, again, if you, I don't think it was a hit, but my claim was that you want to have inter and intra-group interactions, and that's why the block diagonal assumption was unsatisfactory. To me, it's really important to know about cases where we don't have block diagonality. Okay, so that's the kind of quote-unquote the big result. All right, so you should all be, yeah, please.
Is one way to think about this that we should feel really, really good if we can take any sort of credible structural stance on the structure of the network?
Yes.
Yeah, okay. So we should work really hard to get the sort of information that we generally have been acquired.
But we shouldn't be unduly worried, unless you can actually take a stand and say, I'm certain this is literally what the matrix is, then identification is going to, quote unquote, typically hold.
Right. Right, okay, so that's fine. But in particular, the assumptions, we tend to make the linearity assumption. We should really be happier if we were going to make any other assumption.
Oh, absolutely, because the nonlinear models, identification conditions are weaker. Now, all of you should be jumping up and down saying that this is a useless theorem for empirical work. And I told you the reason. Because we typically don't have the data, don't tell us what the darn socio-matrices are. Okay? This linear and means model resolved the problem by assumption. It said, I declare that the weights are 1 upon ng, and within the group and 0 otherwise. Okay? What's the add health data set do? It doesn't tell me the intensities. It tells me, well, it tells me rank orders, which people don't use, but it just gives me the adjacency matrix. In other words, it tells me where the 0s and the 1s are, modulo the restriction that it only could be 5 males and 5 females. You had a question, I'm sorry.
No, it's just a comment that it doesn't because it didn't attempt to, but knowing this, they tended to try and get that kind of thing.
Yeah, well, I mean, one message is that would be incredibly valuable data. But nevertheless, since we don't have the data, and I think making the assumption, the ad hoc assumption to be blunt, that the weights are all equal and have this block diagonal structure, naturally the question you ask is, well, what we can do if we don't know? Well, we've got to be a little careful on what it means not to know. If I know nothing, in other words, I'm not willing to make any assumptions outside the existence of an equilibrium, which kind of says other data, there must be that was fulfilled. You already know the answer is I can't say anything, because that would be the classical simultaneous equation system with no exclusion restrictions. All right? So the real question is, how do we characterize partial knowledge of the social network? In other words, is it possible that I could know something about the social network and achieve identification? Okay, that's where the frontier is. So, yes?
So, I don't know if this is possible, but it could be any way in which I can recover the preference of individuals about how they form networks. For example, suppose that I live in this very simple world in which I just care about how far is my friend and how rich he is. And I just care about the difference between the distance and the difference in income. So I could like specify this.
So it's not only a great idea, it's going to show up in 2 slides. Okay, so I don't mean to interrupt you, but he's going to yell at me, and so I'm just going to ask, let me get to it. So the add health, you could say, has partial information in it because it tells me where the 0s are in the matrix. So the right way to think about the add health is it's useful not because it tells me who the friends are, but if you believed that that was sufficient for the friends, it tells you who isn't friends with you. That's really valuable because after all, if you and I are friends, and the 2 of you are friends, but you don't know who the hell I am a great instrument for for your effect on his behavior. So what this paper and the paper I emailed Martin do is they basically begin to sketch out what I'm going to call the assumptions possibilities frontier. Yeah.
The other cool thing about ad health is that they collect the transcripts, so you can see what classes people are in,
Okay.
and how consistently they're around each other for class.
Yeah. No, okay. Yeah. So that type of data one would want to bring to bear because that gives you something about dynamics, who's kind of repeatedly together versus it's more transitory. Leonardo's question was the following. Maybe I have a theory that says the intensity of the relationships between the agents depends on distance. Well, what that would do is it would say that I metrize the A matrix as a function of a finite set of parameters. Okay, the simplest one would just be to say there's a geometric, think of everybody in a circle and there's a geometric decline in intensity. For that case, that would be the matrix. Now we're back in a world where we could talk about identification again. And so for that particular case, now you've got to be pretty careful about theorems. Because what happens is, for that particular model, what you have is something called complete identification. and what it says is, okay, that's a bunch of, let me just say what it says. You need 4 groups of different sizes. Suppose that that's true. I'm sorry, you need at least 4 individuals in this population. I misspoke. What you can show is, actually, the model isn't identified, but it has a property called complete identification, which means that there's a finite number of parameters that are consistent with the system. And you can show the cardinality is actually 2 times the population size minus 1. Okay, so that's kind of an esoteric sounding theorem, but it's an example of how you would begin to make progress with partial network information. Another form of partial network information, as I said, is if you had a data set where you literally knew who didn't know somebody, you know, people that were strangers, those you really can credibly say are zeros, then those become exclusion restrictions in the classical simultaneous equation sense. And obviously I could pursue other directions there. So in my view, maybe the way I want to summarize the lecture, since we are out of time, the lecture notes go through partial identification in the presence of unobserved group effects for binary choice systems. All of the ideas come down to one idea, which is if you observe 2 groups, one's fundamentals say they ought to be doing better than the second group, and you see the reverse, what we call a pattern reversal, that can give information about the presence of social interactions, that those interactions are kicking the group above what the, quote, fundamentals would suggest. So if you see an inner city school with an incredibly high graduation rate, that's probably a good sign that something good is going on there in terms of how people are being influenced. Okay, but I go through that in the notes. Brock and I published a paper in 2007 that talks about the identification conditions in painful detail, and I promise you it was painful. But what I want to say is, for me, the real frontier is asking the question, under plausible assumptions about information on networks, as in we know nothing, but we don't actually know the sociomatrices, what can we say? Now, Leonardo sort of gave the first best answer, is that if we can model the network formation process, then that, of course, means we're back in the self-selection analogy, which is expand the domain of decision-making that we're modeling, and that's going to facilitate identification. I'm asking a more modest question, even for, you know, where we're not able to model that process, what partial information would let us say something about the presence of social interactions. And so the only 2 papers that have done it are this handbook chapter and then a working paper by Bloom, Brock, myself, and Raji Jayaraman, who's a assistant professor in Germany, and I want to be clear that she deserves full credit as a co-author, even though she's an order of magnitude younger than the balding characters on the paper. That has another set of results of this form about what you can do with partial knowledge of the networks. But all we have done is sketch out little pieces of the assumptions possibility frontier. I think there's just an immense amount more to do. And I even think I could imagine dissertations on such a subject. Okay, so let me stop there. Thank you for your attention.